This video will describe how industrial pneumatic systems work. These 5 types of components represent the most common elements used in these systems. The ultimate goal of this entire collection of components, in most cases, is to create motion that will do some type of work in an industrial setting. Pneumatics is one of the most widely used technologies to automate repetitive processes. Some common applications might be to move product from one place to another, or to press or clamp pieces of a product together. To best understand how the system works, we will start at the beginning with the compressor and follow the process through to the end goal of motion. The compressor generates the energy that powers the system in the form of compressed air. In order to generate compressed air, the compressor draws in atmosphere from its surroundings and squeezes it or confines it into a smaller space, creating the energy needed to drive the system. Once compressed, the air needs to be dried and cleaned so that harmful particulates such as rust or dirt does not clog up the moving parts in the system. The compressed air will travel through a tube or line to the next component, called an air preparation unit, or FRL. FRL is short for filter, regulator, and lubricator, which are common pieces that make up the air preparation unit. Typically, the first unit in the air preparation system is what is called a bulk liquid separator, which circulates or spins the air using specially shaped vanes. The rapid circulation of the pressurized air sheds unwanted moisture due to centrifugal force. The next unit is a filter, which further removes particulate and moisture in a 2-stage process. Just like in the bulk liquid separator, a series of vanes or louvers in the filter circulates the air in the first stage. In the second stage, the air passes through a screen of sorts, called an element, in order to catch unwanted debris. Once dried and cleaned, it is common to adjust the level of air pressure coming out of the compressor. This adjustment has an impact on how much force the system generates. Higher pressure allows the actuator to put out more force, and lower pressure creates less force. The regulator achieves this using a spring-loaded assembly. The knob on the regulator adjusts the force of the control spring to achieve a desired pressure set point. Whenever the downstream pressure level drops lower than the desired set point, the poppet, or internal valve, opens a pathway for the higher pressure upstream to flow downstream. This continues until the pressure in the system reaches the regulator's set pressure. At this point, the poppet or internal valve closes until there is a new downstream demand. It is also common to have a pressure gauge on a regulator so the user can monitor downstream pressure. Finally, in specific applications, such as air motors or pneumatic tools, a lubricator can be added to distribute a fine mist of lubricant into the compressed air to help lubricate downstream components. Now that the compressed air is clean, dry, and set to the correct pressure for the application, the next step is to direct it where to go to create motion. A directional control valve is used to achieve this task. This directional control valve has a series of internal pathways that can connect the air coming into the inlet port with one of 2 avenues to leave the valve, called working ports. Depending on the position of the moving element, which is typically called a spool, the air will be blocked from traveling down one pathway and allowed to travel down the other. The high spots on the spool, called lands, will block the air from proceeding down one path, while the lower sections on the spool, called grooves, will allow air to flow around them and proceed to one of the working ports. In this common type of valve, when the unit is not activated, the spool is forced to the left side of the valve by a spring. In this position, you can see that this land blocks air from going out the number 4 working port, and instead is forced to go out working port number 2, because the grooved lower section of the spool allows air to flow past it and out to the number 2 working port. In order to change the direction of the air to the number 4 working port, the valve needs to be turned on. In most automated equipment, a PLC, or programmable logic controller, will instruct the valve to shift using an electrical signal. When the signal arrives at a portion of the valve called a solenoid coil, a magnetic field is created that pulls a cylindrical piece called a plunger towards it. When that plunger is unseated, it allows air from inside the valve, known as pilot pressure, to push the spool to the right. Once the spool reaches the far right side of the valve, the lands or high spots are now closing off the passage to the number 2 working port, and instead directing the compressed air to flow to the number 4 working port. When the signal from the PLC is removed, the force generated by the electromagnet is also removed, at which point the spring on the plunger returns it to its normal state. which removes the air signal that is pushing on the spool. The spring on the opposite end will return the spool to its default position once again, directing air back out the number 2 working port. The PLC can now direct air to whichever port is needed whenever it is needed. The next component in the system, the actuator, will allow us to do some useful work with the air we compressed, cleaned, and redirected. In most applications, the purpose of changing the direction of the compressed air with the valve is to cause motion in different directions. Parker makes a wide variety of actuators, or cylinders as they are also commonly called, that will convert compressed air into motion. The most common type of cylinder is the rodded variety displayed here. The actuator will create motion using the energy of the compressed air that is supplied to it by the directional control valve. We can see that the working port number 4 is connected to the back or cap end of the cylinder. When the compressed air pushes on the piston, it is forced to move forward inside a hollow cylinder that is commonly called the body. The piston is attached to a rod that will extend as a result of the force generated by the compressed air acting on the piston. The actuator will continue to move in that direction until it reaches its physical limit, or if the force resisting motion, commonly called the load, is higher than the force of the compressed air, in which case the pressure regulator could be adjusted to a higher pressure. Now that we have completed the extension, we will need a method to retract the actuator to its original position. The directional control valve will achieve this by changing the direction the compressed air flows from number 4 working port to the number 2 working port. The number 2 working port is connecting to the head end of the actuator, and when the compressed air pushes on the opposite side of the piston, it will reverse the direction of the piston rod assembly. This reverse motion is typically referred to as retracting. For this actuator to retract, the air that is already filling the cylinder needs to go somewhere, which is commonly referred to as exhausting. The exhaust air is illustrated by the red color and is shown exiting the cylinder and flowing back through the valve, out the muffler to the atmosphere. This system can repeat this process as often as the PLC tells it to move things from point A to point B in one example. In this example, the PLC is telling the actuator to move this product by sending a signal to the directional control valve, which is using the clean, dry compressed energy to power the actuator. Pneumatics are also commonly used to press 2 components together in an assembly process to help form a finished good. Through the combination of Parker's air preparation, valve, and actuator products, there's a wide range of applications that can be solved. Visit us at parker.com to explore all of the pneumatic products we have to offer.